Okay, so it's our buffer one. We all love these. So, key thing, let's just think this one through. Let's not triangle over it. The student decided to use 0.200 moles precipitate of phenol mixed with an equal volume of sodium phenoxide. I need to determine the concentration of sodium phenoxide that the student would need to mix with that. Right. First of all, start off with your Ka expression. I'll just use A minus to represent the conjugate base. What do I know? I've been told the pH, so I can work out the concentration of H plus as being 10 to the minus pH, 10 to the minus 8.71. Let's do that. Minus 8.71. That gives me 1.95 times 10 to the minus 9. Okay, I know that boy. Do I know Ka? Yeah, I do, because they told me that earlier in the question. That is 1.3 times 10 to the minus 10. That equals H plus, which we've just worked out as being 1.95 times 10 to the minus 9 times the concentration of A minus over the concentration of HA. Okie dokie. I've been told the concentration of the original phenol solution. Is that going to be the case? It's told me that it's going to be mixed with an equal volume. So if it's mixed with an equal volume, that in the buffer is going to become 0.100 moles per deciliter because I've diluted it down by half. So you've got to take that into account. So that is going to become, I can now work out that one. So I'll put that on 1.3 times 10 to the minus 10, 1.95 times 10 to the minus 9 times the concentration of A minus, which I'm trying to find, over 0.100. That's the one I want to find. Concentration of A minus is going to be 1.3 times 10 to the minus 10 times 0.100 over 1.95 times 10 to the minus 9. Right, into our old calculators. Again, I will, well, it's not too bad. That's just going to become 1.3 times 10 to the minus 11. Yeah. Divide that down by 1.95 times 10 to the minus 9. That gives me it as being 0.006 moles per decimeter cubed. But that is in the buffer solution. They want the original, so I need to times that by 2 because it's the original solution before I diluted it down by half. So the original concentration is 0.006 times 2, which gives me 0.013 moles per decimeter cubed. Right, now this, ironically enough, well, it's a little bit like organic chemistry. So remember, this is synoptic. You need to remember a little bit of your organic chemistry here. Structure, identify a chemical that I can add to this to make a buffer solution. Well, you've got various ways. If you assume you're going to add, so if you add, you could add sodium hydroxide, and that would, remember, well, we just talked about it, phenol is a weak acid, and so will react with sodium hydroxide, so that would give you that salt there. You know, I'm just taking a guess that it's going to remove that hydrogen. It could equally remove that hydrogen. You'd have to add quite a lot to remove both, in which case it's unlikely. But you would certainly, that would produce it. Or you could just add that one. They don't mind. But Adding sodium hydroxide would give you that chemical. Just you do need to remember you only add a small amount of that. That's got to remain in excess because you need both of these here in the solution to have a buffer. Okay, so syngas. A little bit of information about it. Dynamic equilibrium, surprise, surprise, and it's in a 2 decimeter cubed sealed vessel. Give me the most 2 features of a system that's in dynamic equilibrium. Well, you know, the macroscopic properties will not change, so that's the overall concentration of carbon monoxide, hydrogen and methanol. They do not change. The other one that you can mention is the rate of the forward reaction is the same as the rate of the backward reaction, of course. Write an expression for Kc. Kc is going to equal your concentration of methanol divided by the concentration of carbon monoxide and the concentration of hydrogen squared, because it's got a 2 up there. Calculate Kc. So we've just got to bung those numbers in, haven't we? 5.2 times 10 to the minus 5 for that boy. And then I've got carbon monoxide 6.2 times 10 to the minus 3 and 4.8 times 10 to the minus 2, remembering that is squared. So again, I know I go on about this, but I really would always calculate these values before trying to save yourself 10 seconds and messing it all up. Saying that, I'll probably do that myself now. So that equals 5.2 times 10 to the minus 5 divided by 1.428 times 10 to the minus 5. So let's just finish that calculation off, and that comes to 3.64. I also need to work out my units for that. So let's do that. I completely stuffed that up. Let's do it again. Right, so now it's time to calculate, to write Kc and then calculate it. So Kc, fairly straightforward for us by this stage. So concentration of methanol divided by the concentration of carbon monoxide and the concentration of H2. Remembering, of course, that H2 is squared because you've got 2 moles of it up there. Calculate Kc. Right, first thing we need to convert these moles into concentration. So let's do that. 6.2 divided by 10, so if I just write it underneath, that's going to become 3.1 times 10 to the minus 3. That's going to become 2.4 times 10 to the minus 2. I should be able to do that, but I can't. That becomes 2.6 times 10 to the minus 5. So they are my concentrations. I've divided it by 2 because that is the volume of the container. And remember, these are concentrations. So now I put those numbers into Kc. So that becomes 2.6 times 10 to the minus 5, 3.1 times 10 to the minus 3, times 2.4 times 10 to the minus 2 squared. Right, let's put those into our calculators. I know you kind of think, oh, this is a waste of time. But it is useful to practice putting these things into our calculators, only because I've seen and marked so many papers where they have stuffed up just putting it into their calculator. And it's understandable, you know, you're stressed out, time and everything, but really, really easy to lose the final mark on that. So I've got that, so let's do that. 2.6 times 10 to the minus 5 divided by my answer. That gives me it being 40.56. Okay, so we've got that now. I now need to work out my units. Unit-wise, it's going to be moles per decimeter cubed divided by moles per decimeter cubed. That's going to become squared. So my units are moles to the -2 decimeters to the 6. Oh, right, so for this next one, I've just popped the equation up here just for minus. So the pressure was increased whilst keeping the temperature constant, and we left it to reach equilibrium, and the position shifted to the right. Why? Well, this side I have 3 moles of gas, but that side I've only got 1. Therefore, we can say 3 moles of gas went to 1 mole of gas. If you increase pressure, equilibrium shifts to side with fewest moles of gas. What is the effect of Kc? Nothing. Kc only changes with temperature, so there is no effect. Kc only changes with temperature, and it's worth always stating that just in case that's what they're looking for. Okay, temperature was increased whilst keeping the the pressure constant, and we left it to reach equilibrium. The value of Kc decreased. Explain what happened to the equilibrium. Well, if we go back to our equilibrium, carbon monoxide plus 2H2 goes to CH3OH, yeah? Okay, Kc, concentration of methanol, this is going to be short as a problem, times concentration of carbon monoxide and the concentration of H2 squared. Kc has decreased, therefore it has shifted. This has got smaller, this has got larger, smaller, larger. So the equilibrium has shifted to the left-hand side. So we can say equilibrium shifted to left-hand side. So what can we say? Well, when we increase the temperature, the equilibrium shifts in the endothermic direction, and therefore the forward reaction, delta H, must be negative. It's exothermic. Okie dokie. Write an equation for the complete combustion of methanol. Let's do it. Don't forget oxygen. If it's complete combustion, it makes carbon dioxide and water. You've got 1 carbon there, so let's make 1 carbon there, 4 there, so I'm going to make 2 waters there. Then I worry about my oxygen. I've got 4 here, 2 and 1 there, so I've got a total of 3 here, so I need 1.5 O2s to get that to balance. Why do we reckon methanol is antispectral? Well, if you have a look at it, it's got an extra oxygen in it. So compared to a hydrocarbon, which doesn't have any oxygen in it, this is going to be better. So he will promote efficient combustion, more efficient combustion, because he can supply oxygen.